Okay, so we're going to do problem 9.44, and we're going to do a problem completely symbolically until the very end in part B. Okay, so keeping in mind we're in chapter 9, so we're using energy methods. That means using work and energy as opposed to Newton's second law to solve the problems. Okay, so we have a crate, mass M. Okay, so that's a given. Even though it's just a letter, it's just a symbol, it is assumed to be a known value that's given to us. And we have a frictionless slope. Okay, that makes it a little bit easier. We have angle theta. Oh, we have a horizontal force that is pushing with magnitude F. Okay, so we're pushing this crate up this slope, but we're pushing on it horizontally. So our force looks like this. It's not up the incline, it's horizontal. Okay. And we know the magnitude. So we want to use work and energy to find expression for the crate's speed, v, when it is at height h above the bottom of the slope. Okay. So we need to use work and energy methods. So let's start with the work kinetic energy theorem. So any work that is done is going to cause a change in the kinetic energy. And the kinetic energy, as you recall, involves the speed. So this is going to be 1/2 mv final squared minus 1/2 mv naught squared. And in this case, we know that we're starting from rest, so the initial velocity is 0, which means that whatever work is done is going to be turned into the kinetic energy that we see at the end. And it's this final velocity that we are asked to find. All right, so if we can determine the total work, then we can easily get at that final velocity. Okay, so let's find the total work. All right, well, to do that, we better draw some more forces. Let's get all the forces that are acting so we know how to calculate the work done by each of those forces. Okay, well, let's see. I know that there's weight and there's the normal force. There's no friction, so that would be the three forces. That's all the forces we have. Okay, and we've got our ramp angle. Okay, so let's find the work done by each force individually, just like we did in the previous problem. Okay, so let's find the work done, work done by the normal force. Okay, so remember when we draw our diagrams, we draw the force and then we draw the displacement. Yes? Okay, so the force is going to be up this way. Now think about the displacement of the box. The displacement of the box is along the ramp, yes? So it's going to be like this. So here is our delta R. And let's think about the angle here. Because this is the normal force that's perpendicular to the ramp, this is going to be a 90-degree angle. Okay, so let's just move that over there. Okay, so work done by the normal force is going to be the force of the normal force dotted into the delta R. Okay, so that means this is going to be the normal force times delta R times the cosine of the angle between them, which in this case is 90 degrees. Okay, so the cosine of 90 degrees is 0. No, I'm sorry, that's 1. Yep, my brain is dead today. Let's see. No, it's 0. Yep. It's that kind of day. All right. So because this is 0, this says that there's no work done by the normal force. Well, that should make sense considering that only the component of the force that is in the direction of the displacement is going to do any work. Well, there is no component of the normal force along the ramp, so no work is being credited for to the normal force. Okay, so let's look at the weight. Okay, so work of, now this is going to get a little confusing with the W's. This is work of the weight. Okay, so let's draw the diagram. So we have the force of the weight, and then we have the displacement, delta R. Here is the phi that we need. All right, well, we don't know what that ramp angle is, so how are we going to add 90 degrees to it? Well, how about we do something like, let's redraw this. And I'm going to break this up into 2 separate angles. So I'm going to call this one 90 degrees, and I'm going to call this one theta. Because, well, that's the ramp angle, yes? Okay, so this angle phi is 90 plus theta. All right, so the work done by weight is going to be F dot delta R. So that's going to be the weight times delta R times the cosine of this angle. Okay, so I'm going to make this, I'm going to turn this, let's make this weight here, make it like really small so it's clear. This is work and the little one is weight. Okay, so maybe I should label that more clearly. Okay, so this one is work. This one is weight. Okay. So the weight is mg. Okay, and then delta R and my cosine, and I'm going to call this theta plus 90. Maybe that looks gross right now, but we have a trig identity for that. It'll just clean it right up. Okay. So, in fact, why don't we pull out the trig identity now? Okay, so I'm just going to do a little inset here. So, in general, we can say that the cosine of A plus B. Now, I would not expect you to memorize this or have this readily available. It's just one of those things that because it's not on an exam, we can just do it and learn from it. I would not expect you to do this on an exam. Okay, so this is going to be cosine A cosine B minus sine A sine B. Okay, now let's substitute. Cosine theta plus 90. Okay, so that's going to be cosine theta cosine 90 degrees minus sine theta sine 90 degrees. Okay, so the cosine of 90 degrees, that's 0, so that whole term goes to 0. Then the sine of 90 is equal to 1. So all of this turns out to just be equal to negative sine of the angle, of the ramp angle, theta. Okay, so we can make that substitution in our expression here. So mg delta r, and this is the negative sign, so I'm going to make that negative. Okay, so negative sine theta. Okay, so I made that substitution. So that is the work done by the weight. Okay, so let's see, we've got the work done by the normal force, the work done by the weight. Now we need the work done by the pushing force F. So let's find that one now. Okay, so I'm just gonna circle this one so I find it easier. All right, so now the work done by F. Okay, so the diagram is, here's F, here's the delta R, and now the angle between them is the ramp, it is the ramp angle. Okay, so we're going to list our things over here. Okay, so this is going to be F dot delta R. Okay, so it is just, F, whatever that is, delta R, and then it's going to be the cosine. In this case, it's just theta. Yes, it's phi, but phi happens to be theta. All right, well, that was pretty straightforward. Now, let's get the work total. Okay, so this is going to be the work done by, work done by the normal force, plus work done by the weight, plus work done by the force F. Okay, so that's 0. Work done by the weight is minus mg delta R sine theta. The work done by the force F is F delta R cosine theta. Okay. Let's get delta R in terms of the height h, because they were asking us in the problem, they want to know, find the crate speed when it is at a height h above the bottom of the slope. Okay, so let's go and draw this diagram. Okay, so if it is at some height h, okay, so this is h, this is delta R, here's our angle here. We know that h is going to be delta R times the sine of theta. And solving for delta R, that gives us h over sine theta. So I'm going to make that substitution for delta R in my expressions up here. Okay, so my work total is going to be minus mg. Now my delta R is h over sine theta. Okay, and then also we have the sine theta. Then F, h over sine theta, and then cosine theta. All right, well, these sines cancel. So we get mgh. And then over on the other side, we can write this as fh over tangent theta. Okay. And we need to find, let's see, okay, so, okay, all of these are givens. All right, so h is a given, f is a given, theta is a given. All right, all of this is known. So now we're ready to go back up to our expression up here. Remember how we were trying to find what that total work was so that we could put it into the work kinetic energy theorem. Okay, so we can find that final velocity by knowing this total work. So let's go back and put it up into that expression there. So now work total equals 1/2 mv final squared. I'm going to put that down here. Okay, so work total equals 1/2 mv final squared. That's what we determined up above. Actually, I'll just write the whole thing out here just so we're super clear. All right, so let's plug in. So work total is all of this stuff from the previous step. And that equals 1/2 m v final. I'm just going to call it v, not v final, v squared. All right. So now I'm trying to solve for that velocity. So let's do that. Okay, so that's going to give me all of this stuff. Okay, and then divided by 1/2 m, and don't forget the square root. All right, let's see. I think that is it. That is an expression. It's not beautiful, but it is an expression. Okay, I'm going to go with that. So here's my expression. That's for part A. Let's look at part B. Part B says, all right, well, now you have Doug, and Doug has his numbers with him. So we're going to use these values. So we have a 25 Newton force for the force F, 5 kilogram crate, 2 meters high, 20-degree slope. All right, let's see. Let's write all this down. Okay, so now we know that M is equal to 5 kilograms. We know that H, I already forgot. All right, so 2 meters. Okay. 2 meters. F is 25 newtons, and the angle is 20 degrees. Okay, so now let's plug all those things in and see what we get in our expression here. Okay, so I'm going to start with my expression, always recopy it. Okay, and then we're going to plug into it. Okay. Wait, is that 5? I just want to make sure that I have the right numbers in here. Yes, okay, good. All right, so 5 kilograms. All right, then gravity squared. Okay, then the height is 2 meters. Then we have 25 newtons and another 2 meters over tangent of 20 degrees. Then we have 1/2 times 5 kilograms on the bottom and square root all of that. Okay, so let's see how this goes in the calculator. All right, so I get a speed of 3.968. I'm going to call that 4.0 meters per second. Boing.